condensation polymers. Condensation polymerization involves two different types of monomers, each with at least two functional groups. Each functional group reacts with a group and another monomer, forming a link, creating polymer chains. Now, obviously, definition of condensation polymerization isn't really that important to memorize all these reactions and equations. But yeah, still memorize it. It involves two different types of monomers, each with at least two functional groups. Each functional group reacts with a group on another monomer. It involves two different types of monomers, each with at least two functional groups. Each group reacts with a group on another monomer, form a link, creating polymer chains. Examples of condensation polymers: polyamides, polyesters, polypeptides. Every time a link is formed, a small molecule is lost. Water, its most common one, therefore it's called condensation polymerization. Why do long chains form? Dicarboxylic acids and diamines have functional groups at the end of each of the molecules, therefore long chains form. Carboxyl groups of dicarboxylic acid reacts with the amino groups on diamines to form an amide link. So your dicarboxylic acid, HOC-O or C-O or H, dicarboxylic acid, plus your diamine, NH2 R-NH2. And what happens is the OH from the carboxylic acid, your H here, water is going to be eliminated, or H2O, and then you just carry on. So HO, C-O, R, C-O. So if that's gone, you join these together, you got this N goes there. There you go, C-O, NH, R-NH2. And that's called your amide link when you see the C-O and your NH. Nylon 6,6 is a polyamide made from 1,6-diamine or hexane and hexane dioic acid, used to make clothing, carpet, rope, airbags, and parachutes. You don't need to know all the uses, but just a couple. 1,6-diamine or hexane, so amino, so I'm going to have H2N, NH2, NH2, and then because it's hexane, so we're going to have CH2, N here plus your hexane dioic acid, C-O, HO. Hexane, I've already got a carbon here, so it's not going to be CH2, it's going to be CH2, because I've already got two carbons there, so I need 4 to get overall 6, CH2, C-O, OH. Same thing happens, this H and this OH goes. But then in this case, what also can happen is that this OH and this H goes, so then you get NH, CH2, NH, C-O, yes, and then your CH2, C-O. Nylon 6,6 this is, and there's your end here, plus your 2 NH2O. So nylon 6,6, a polyamide made from 1,6-diamine or hexane and hexane dioic acid. Now I'm going to start creating a lot of YouTube shorts, and I will be going through definitely this topic, because this is one of my weakest year 2 topics for sure. It's just about memorizing them, and it's just a bit annoying when you haven't memorized them. So Kevlar is a polyamide made from 1,4-diamine or benzene and benzene 1-1,4-dicarboxylic acid. Kevlar polyamide made from that, using bulletproof vests, boat construction, car tires, and lightweight sports equipment. So 1,4-diamine or benzene, pretty simple. You got your benzene ring, you got an amino group on the first carbon, NH2, amino group on your fourth carbon, NH2. On either side, right? And then you've also got benzene 1,4-dicarboxylic acid, same thing, C-O, HO, benzene ring, C-O, OH. What happens though is same thing as that. OH from your carboxylic acid, this H, that's going to leave water molecule, and again this hydrogen and this OH can leave. So you're going to have NH, your benzene ring, NH, C-O, Kevlar, your benzene ring, and then your C-O, N plus 2 NH2O, and this is called Kevlar. The carboxyl groups of dicarboxylic acids can also react with hydroxyl groups on diols, forming ester links. Polyesters, polymers joined by ester links. Dicarboxylic acid, HOC-O or C-O-H. Diol, HO, and I'm showing each one, H-O, R-OH, diol. And what happens, OH, dicarboxylic acid, H in the diol, that leaves water molecule. And yeah, so you got your C-O, R, C-O, O, R-, your ester link, O, and your H plus H2O. Now I did draw a circle on this, but I did cross it off because this is just an example to show you. In the real life, like, this is just a template to work off. In these examples, yes, then this also happens, but in this case, no. I'm just showing you plus H2O. Terylene TMPET formed from benzene-1,4-dicarboxylic acid and ethane-1,2-diol. Used in plastic bottles, clothing, sheets, and sails. Benzene-1,4-dicarboxylic acid, C-double-bond-O, HO, benzene ring, C-double-bond-O, OH. Ethane-1,2-diol. Ethene, obviously your diols, your OHs, is obviously going to be at the end of these carbons. Not going to be here, because then that's, you want them to be so they can, a water molecule can be eliminated. So this OH and this H leaves, and this OH from the carboxylic acid and this H from ethane-1,2-diol leaves. And what you're going to form is, this OH from the diol and this H from the benzene-1,4-dicarboxylic acid leaves. So you form C-double-bond-O, benzene ring, C-double-bond-O, CH2, because it's an ester link. It's terylene and you N plus 2 NH2O. Condensation polymerization. What is condensation polymerization? Condensation polymerization involves due to two different types of monomers, each with at least two functional groups. Each functional group reacts with a group on another monomer, forming polymer chains, forming a link creating polymer chains. Involves two different types of monomers, each with at least two functional groups. Each functional group reacts with a group or another monomer to form a link creating polymer chains. So it can be reversed by hydrolysis. Water molecules are added back in and links are broken. So here's what the first thing you need to identify. What kind of link is it? Is it amide link, ester link? Which one is it? So in this case, it's an ester link, C-double-bond-O NH. It was C-double-bond-O O, then it'd be ester link. But in this case, amide link. So how do I form an amide link? Carboxyl groups of dicarboxylic acids can react with hydroxyl groups. They can react with amino groups and diamines. So I know I'm going to form carboxylic acid. I'm going to form a diamine. And that's how you would do it. So I'm going to be like, okay, so I'm going to split it in half. So the amide link split in half, and I'm just going to add what would be left. So because this part got C-double-bond-O, well, it's going to be dicarboxylic acid. So I'm going to have a HO here, OH here. In this case, I've got R-NH. NH, well, I'm going to have diamine, so we're going to be NH2, R-NH2. N plus your N, and remember to show the N's plus 2 NH12. Why are condensation polymers stronger / more rigid than addition polymers? Condensation polymers made up of chains containing polar bonds, as well as van der Waals forces, that are dipole-dipole forces, and hydrogen bonds between the polymer chains. They have polar bonds and chains, so open to attack by nucleophiles, therefore biodegradable. Examples of addition polymers: polyethylene, polyalkenes, made up of non-polar carbon chains, therefore unreactive and inert. Polystyrene, because they're made up of non-polar carbon chains, therefore unreactive and inert, they won't react. However, they are non-biodegradable. Plastics, waste plastics can be buried. Now, before I carry on with this, because this is just a whole load of, it's not that, it's very important as well to learn. But before I carry on with that, if this was an ester link, C-double-bond-O, then what would happen? Well, then you're adding water to NH2O, same thing, reversed by hydrolysis, water molecules added back in, links are broken. But what's going to happen is, instead, because you're forming, you've got an ester link and you want to reverse it, carboxyl groups of dicarboxylic acid react with hydroxyl groups of diols, forming ester links. So I'm going to form dicarboxylic acid and a diol. That's how you would do that. A diol HOR-OH. So waste plastics can be buried. Landfills used when it's difficult to separate from other waste, not in sufficient quantities to make separation worthwhile, too difficult technically to recycle. Landfill, cheap and easy, but requires area of the land. As waste decomposes, it can release methane, plus the leaks from the landfills can contaminate water supplies. Waste plastics can also be buried and heat used, burned. Waste plastics can be burned and the heat used to generate electricity. Process needs to be carefully controlled to reduce release of toxic gases. Waste gases from the combustion pass through scrubbers, which can help neutralize gases, HCl, by allowing them to react with base. But the waste gases still contribute to greenhouse effect. Recycling plastics reduces the amount of waste going to landfill, saves materials vital as oils are non-renewable. Cost of recycling plastics is lower than making the plastic from scratch. Produces less carbon dioxide emissions than burning plastic. However, it's technically difficult to recycle plastics. Plastic can be easily contaminated during the recycling process. Collecting, sorting, processing plastics is more expensive than burning them, and you can't make plastic you started with.